Hello everyone, I'm Yang Zhang, a PhD student from University of Connecticut. My advisor is Professor Jung Chang. My poster is titled as Inverse Analysis for Damage Identification using MOPSO. There are four parts. The first part is problem descriptions. The goal of this research is to utilize piezoelectric actuator to detect damage in railway track. So in this research, we demonstrate the damage detection and identification mechanism. So as shown in the figure 1, the PZT transducer is attached to a metal plate. So when voltage is applied, the PZT patch can serve as an active sensor to acquire the admittance data. In this data, the damage information is included. And from the admittance change responses of the system, we can find the damage location and severity inversely. And this inverse process can be converted to an optimization problem, which is solved by multi-objective particle swarm optimization algorithm, the MOPSO. Second part is admittance data. As we mentioned before, we need to use the admittance data to conduct damage identification. Here, the admittance change is defined as delta A equal to S multiplied by alpha. The S is sensitivity matrix, which is obtained using the finite element analysis. And alpha is damage index vector. So as shown in the figure 2, if there is damage in the structure, the admittance curve will have a shifting peak around the resonance frequency. So as shown in the red curve, so by comparing the black curve and the red curve, the black curve is healthy state, the red curve is damaged state, we can get the admittance change. In this limited shifting area, we can get the endpoint, and this endpoint will be used to conduct damage identification. A third part is the inverse problem definition. Since the simple data points are limited, what it means that the m is far less than n. Here n is the unknowns. The matrix inversion for S is prohibited, or it means that S is a matrix that without full rank, so we can't do the matrix inversion. So in this case, we convert the inverse process to an optimization problem. In this optimization problem, we have two objective functions. The first objective function is comparison between admittance changes. Simply speaking, we can use the finite element analysis to get admittance change. We can also use the experimental method to get admittance change. And by comparing these two and minimize the differences, we can find the damage location and severity simultaneously. And also, as we will know, the damage in the structure can only affect a small area. So the second objective is defined to determine the sparsity of the damage index vector. And then the MOPSO algorithm is used here due to its simplicity and flexibility. So as shown in the figure 3, each particle xi can move towards to the global best G best based on the two trajectory expressions, the Vi and Xi. The initialization method for the algorithm is devised as a grid space, so the particle can search only at the intersection point of that grid. This development is suitable for this optimization defined here because it includes a discrete objective, the L0 norm. The fourth part is result and discussion. The testbed structure is divided into 25 segments for the purpose of damage identification. Two damage cases are studied. The one case with damage severity of 0.28% at segment 15, the one case with damage severities of 1% and 2.8% at segments 8 and 13 respectively. The identified results are shown in Figure 4. The algorithm identifies the damage location with high accuracy for both of cases, and these results demonstrate accuracy and robustness of MOPSO, or piezo admittance-based damage identification, and these methods can be directly applied to the railway track. And finally, we thanks for the sponsors. And this research is supported by the TIDC at the University of Maine under grant from the U.S. Department of Transportation's University Transportation Centers program. Thanks all. Thank you.